Let's continue from where we left off today and start with example number 1. Example 1 says, what's the inverse of a relation that's represented by this set of ordered pairs? So can we write the inverse as a set of another ordered pairs, as a mapping, and graphically? So we know that an inverse just undoes a function. So in our original function, we input a 1 and we output, or what comes out, is a 5. The inverse is going to be the function where when we input a 5, we get out a 1. Same with this point here and all these other points. We're going to reverse the input and the output. So let's actually just go ahead and write this as a mapping to get started. So if I put all of my elements of the domain in here, of my original function, and all of the elements of my range in here, this is going to be our original function. Let's call it f at x. So if we go through this, we have the elements of our domain are 1, 2, 3, 4, and 5. And the elements of our range are 5, 6, 7, 8, and 9. And as a mapping, it looks like this. 1 is mapped to 5, so when we input a 1, we get 5. When we input 2, we get 6. 3, we get 7. 4, we get 8. 5, we get 9, and etc. So the definition of an inverse is that it's going to undo this, which means our new domain is going to be the range of our original function, and vice versa for the range. So this is going to be for f inverse of x. So in the original function, we put in a 1 and we get out a 5. The inverse is going to start with the 5 and get the 1, which means that in our domain is going to be all of these inputs. So no, these are our inputs. So now we have, in our domain, we have 5, 6, 7, 8, and 9. And so when we put in a 5, I want to get a 1 out of it, and that's going to be the opposite function of this guy here. So the elements of our range are going to be the domain of the original function. So 1, 2, 3, 4, 5. So as a mapping, in the inverse function, when we put in a 5, we got to get a 1. And when we put in a 6, we'll get a 2. A 7 will get a 4. Sorry, a 7 will get a 3. And 8 will get a 4, and 9 would get a 5, which completely undoes the previous function. So if I were to write them out as ordered pairs, okay, so if I were to write this out, and you can write this out yourself if you want to, the new ordered pairs would be 5 and 1, 6 and 2, 7 and 3, 8 and 4, and 9 and 5. Those would be the ordered pairs of the inverse. So let's go ahead and graph these guys. So let's graph the original function first. So there it is graphed. So we've graphed the points 1, 5, 2, 6, 3, 7, 4, 8, and 5, 9. Now let's graph these points here. So we're going to graph the points 5, 1, 6, 2, 7, 3, 8, 4, and 9, 5. So there they are. Here's our original function. Here are the points from our inverse function. And we notice that the reflections of each other in the line y equals x. So here's the line y equals x, and we can see that these two functions are reflections of each other about this line. So imagining that this is our fold line, if we were to fold these points along this line, then they would hit these points right over here. So that's another way that we can prove that these are in fact inverses of each other, because they are reflections of each other in the line of y equals x. So now let's start finding some equations. So the next example says, find the equation of the inverse of each function and sketch the graph of the function and its inverse. Then it says, state if the inverse is a function. Remember that the inverse of a function is not always a function. So let's investigate the inverse, check if it's a function, and if it isn't, let's restrict the domain of the original function so it is an inverse. So we're going to deal with that later if we decide that the inverse is not a function, and then we'll go through that exercise. But here's our function here. This is just a square root function that's been shifted to the right 3. So let's actually make a slight change. I know we were supposed to bring this to the right 3, but let's actually put a plus here just because it's going to visually be a better example for us. We can fit everything that we need to on the graph. Okay, so let's actually change the question to square root of x plus 3. So that we are shifting actually to the left 3. So let's really quickly throw some points onto the graph of what the heck this would look like. So remember, square root function normally starts at 0, 0. The next point is 1, 1. Then we have 2, 4, and 3, 9, and 0, 0, 1, 1, 4, 2, 9, 3, etc. So we're just going to take all those points and shift it to the left 3 this time. So originally we would start at 0, 0, but if we're shifting it to the left 3, we're going to our first point is going to be negative 3 and 0. So it's going to look like that. Our next point, if I just pretend like you're graphing the square root function from there, would be 1, 1, and then we would have 4, 2. So that's where I'm going to start to graph my points. So our next point would be here, and our next point is if we count over 4, 1, 2, 3, 4, and up 2, we have another point here, and then let's keep on going to 9, 3, so 4, 5, 6, 7, 8, 9, up 3, there we go. So let me connect this guy. And here is a very quick sketch of the graph of square root of x plus 3. So we're shifting to the left 3. I know originally it said right 3. We're just going to change it up. Okay, so let's write out these points, because if I want to sketch an inverse, the fastest way to sketch an inverse is just to flip the points. So our original function, f at x, those points are, our first point was negative 3 and 0. Our next point is negative 2 and 1. Then we have 1 and 2. And then, can we count this? We have 2, 3, 4, 5, 6, 7, up 3. So we have 7 and 3. So if we want to very quickly graph out the inverse, all we have to do is flip these points. So one point on the inverse would be 0 and negative 3. Another point would be 1 and negative 2. Another point after that would be 2 and 1. And then we have 3 and 7. So let's sketch that one out very quickly as well. Our new point. So our first point we have was 0 and negative 3. So there we go. Then we have 1 and negative 2. Then we have 2 and 1. And then we have 3 and up 7. 1, 2, 3, 4, 5, 6, 7. So if we connect these now, we're going to have a pretty accurate idea of what the inverse is going to look like. So does it look like we graphed a accurate inverse? So if you can visualize a line y equals x, then you can quickly see that yes, these look to be opposite of each other, undoing each other, they're inverses of each other. So if you can't visualize it, quickly draw the line y equals x. So there's a line y equals x, and we can better see that this red, our original function, is a reflection of this inverse here, or this inverse is a reflection of this function here. So let's just label our graphs really quickly. This was our inverse, and this was our original, f at x. So that's not what the question was asking, though. The question wasn't asking for us to draw the inverse. The question was asking for us to give us an equation of this inverse. But we can predict that this inverse function looks like half of a parabola. So the inverse of this square root better give us some sort of quadratic equation. So let's go back to our equation now. We got to come up with an equation for this blue guy. We have the red guy, the original. We got to come up with the blue guy. Well, what did we do here? The first thing we did to get points from the original function, the first thing we did to get points of the inverse is we flipped x and y. So that's what we can do here in this equation. So if I rewrite this guy, first of all, forget about f at x. Let's just use y. So I have the square root of x plus 3. So the first thing I'm going to do to find the inverse, which is this blue guy, is do the same thing we did with the points. Flip x and y. So instead of y here, I'm going to put x, and instead of x here, I'm going to put y, and then I'm just going to put the function around it. So now, in order to come up with the equation of this guy, we need it in terms of y. So we've got to isolate y by itself so it can look like an equation somewhat like this. So to get y by itself, I got to get rid of this square root. And we know to get rid of a square root, we're going to square both sides. So I'm going to square this side. Let's actually do it in black. So I'm going to square this side, and I'm going to square this side. Okay, so our squared and our square root are going to cancel each other out. So we're left with x squared is equal to y plus 3. So we got to keep getting this y by itself. So we're going to get rid of the 3. We've got x squared minus 3 is equal to y. So our final equation is y is equal to x squared minus 3. So this is the equation of the inverse function, so which is why we can write it as f at negative 1x is equal to x squared minus 3. So let's take a look at this function, and does it match the graph that we came up with? So taking a look at our graph, we have a parabola, well, half of a parabola that's been shifted down 3. And that's exactly what's here. We have a parabola that's been shifted down 3. Now because there's only half, we can make sure that only half is there in the domain and in the range. Let's go on to coming up with the domain and the range of the original function and the inverse function. So let's start off with our original function. Here it is. So the domain of this guy is x as an element of R, but x has to be greater than or equal to negative 3. And for our range, y can take on any value that's 0 or greater. So that's our domain and range of the function, of the original function. Now, because we switched x and y, all of our inputs are now our outputs, and all of our outputs are now our inputs, our domain and range should be switched for our inverse function. So we'll know if we've done it right if we make a domain and range that's the opposite of this guy here, or just the flipped version of it. So take a look at this guy. What values can x take on? Well, x is an element of R. X can be any real number, but it has to be greater than or equal to 0. And if we peek over here, we can see that the domain matches the range of the original function. So we know we've got that part right. Now let's take a look at the range of this guy. So y can take on any values that are greater than or equal to negative 3. And if we peek over, we can see the domain and range match here, and the domain and range match here. So we know we've done it right. The last question we were asked is the inverse actually a function itself? So take a look at this guy here. And does it pass the vertical line test? Yes, it does. So we don't have to do anything else. Let's try one more difficult example. So the original function that we're given is this parabola that's been reflected in the x-axis. It's been shifted to the left 1 and up 2. So let's quickly sketch a parabola it hasn't been stretched or compressed, which makes it easier to draw, that's been shifted left, shifted up, and also reflected. So here are some points on this parabola. So I started with my vertex. It used to be at 0, 0, but shifted left 1 and up 2. And then my next points are going to be, instead of opening up, they're going to be opening down because it's been reflected in the x-axis. My next points would be 1 and 1, negative 1 and 1. Then we would have 2 and 4, 2 and 4, and that's how I got those ones. So that was just a really fast way of transforming. If you need to, just write out the original points of the parabola, transform them that way, that's fine as well. So if we connect these guys, we know we have a parabola that looks like this. And here's our original function. Okay, so now let's come up with the equation, let's come up with some points on the inverse function. So first I'm going to list out the points that we have on our function f at x. So just moving from left to right, we have our first point here is going to be negative 1, 2, 3, and 2. Then our next point is negative 2 and 1. And then our next point is negative 1 and 2. And then we have 0 and 1. And 1 and negative 2. And I just realized this should have a negative up there. Okay, so our first point is negative 3 and negative 2. Our next point is negative 2 and 1. Then we have negative 1 and 2. And then 0 and 1. And then 1 and negative 2. So now let's do a quick sketch of our inverse function. And the fastest way to do that would just be to flip each of these points. So we're going to have our first point is going to be negative 2 and negative 3. So that's going to be a point on our inverse. Then we'll have 1 and negative 2. 2 and negative 1. 1 and 0, and negative 2 and 1. So let's quickly sketch out these points. So once we have our points, let's connect them into a shape that makes visual sense for being the inverse. Okay, so let's label these guys. So this was our inverse function, and this one is our original function. So does this make sense as inverses of each other? So can we tell if this is a reflection of the line y equals x? If you're having trouble, quickly sketch out the line y equals x. So once we sketch out the line y equals x, it's easier to see that these are reflections of each other on the x-axis. Now my parabola isn't perfect. I should have pulled it over a little bit more, and you would have seen it even more clearly that these are reflections of each other. Sorry, that these are reflections of each other. So now that we've drawn the line y equals x, we've shown ourselves that these are reflected in the line y equals x, therefore they're inverses. We flip the points. The hard part now is coming up with the equation for this guy. So this guy looks like two square root functions, one on top and one below. So let's take a look, use our techniques that we learned in the previous example. So first, let's start off with changing f at x to y, just to simplify it a bit. Okay, so just like when we graphed it, we switched x and y, we're going to do the same thing in our equation. So I'm going to put x in the y place and y in the x place, and we're going to put everything else around it. And we've got to get y by itself so that we can see what the equation of this guy is. So we're going to move the 2 over first. So we have x minus 2 is equal to negative y plus 1 all squared. Now we're going to get rid of this negative 1, so we're going to divide both sides by negative 1. And x divided by negative 1, that's just going to be negative x. And negative 2 divided by negative 1, that's going to be 2. So this is going to be the same thing as negative x plus 2 is equal to, and our negative 1s are going to cancel each other out, and we have y plus 1 all squared. So next we got to get rid of that squared, so I'm going to square root both sides, and we are left with the square root of negative x plus 2 is equal to, our square roots are going to cancel, squared and our square roots are going to cancel, we're left with y plus 1. And our final step is we're going to take the square root and take away 1 to get y by itself. So here's our final equation, equals to the square root of negative x plus 2 minus 1. And we know that this is the equation of the inverse function. So instead of y, we can denote y as f negative 1 of x is equal to the square root of negative x plus 2 minus 1. So let's figure out if our equation actually matches our graph. So we have here a square root function that's been shifted down 1. It's been reflected in the y-axis, and it's been shifted, it looks like it's been shifted to the right, to the left 2, but it's actually been shifted to the right 2, and that's because we haven't factored the negative out yet. So if you really want to see that shift, you got to factor that negative out. So take a look at this guy. This top one is definitely the square root function, shifted down 1 to the right 2, and also been reflected in the y-axis because it used to hang out here. But not only that, it seems we have a square root function underneath it as well, which means that there's a problem with our equation. And there's a problem with our equation because we made a mistake. And I don't know if you caught it while I was doing it, but the mistake happened right here. We decided to take the square root of both sides, which means we wrote this square root ourselves. And whenever you're taking the square root of a number, you have to include the positive number answer and the negative answer. So for example, if I were to say that something squared is equal to 4, well, that something squared could be positive 2 or negative 2. So that could be positive 2 or negative 2. So we have to put a plus or minus in front of that square root because there's two possible answers. So all through here we've got to add plus or minus, plus or minus, plus or minus, plus or minus. And so visually what that plus or minus is going to do is plus, if there's a plus 1 in front or just a positive number in front, there's going to be no reflection in the y-axis. So that's this arm right here. And this negative is the graph of the square root function that's been reflected in the x-axis. So we call this guy the positive arm. So that's the equation of the positive arm. The negative gives us the negative arm here, down here. So now we have an accurate equation that matches our graph. So here is our equation of the inverse function. Let's finish off by coming up with the domain and range of both. Taking a look at our original function, the red guy, our domain is x as an element of R. Our range is the highest y value our function can take is 2, which means that y is an element of R, but y has to be less than or equal to 2. Now let's take a look at the domain and range of our inverse, the blue guy. They should be these two flipped, so let's just triple check. Our x can take on any value that's equal to -2 or less. And I don't know why I said -2. It's 2 or less, so x is less than or equal to 2. And then our y values, because we have not just the positive arm but also the negative arm, y can take on all values, so y is an element of R. If we take a peek, we can see that our domain and range of our original and inverse are the same, and our domain and range, or the domain of the inverse, is the same as the range of the original. So we know that we have it right. Woohoo! So the next question asks, is the inverse a function? And if it's not, we got to do a bunch of things to it. Not because we have to, but because the question asks us just to play around with the inverse. So is the inverse a function? Take a look. Well, here's the inverse. It's the positive square root and this negative square root. So is that going to pass the vertical line test? The answer is no. So it asks us to restrict the domain of the original function in order to make the inverse a function. We're going to talk about that together in class, so we're going to put a little pin in it from here. So let's finish off with a couple last problems. So it says the relationship between the speed of a car and its stopping distance can be modeled by the function here. So d is the stopping distance in meters and v is the speed. So take a look at this. This is an increasing function. Let's just make sense of this. So it says the stopping distance and the speed of a car. So just think about it. If someone was traveling in a car really slowly and they had to slam on the brakes, their car wouldn't take very long to stop at all. But if someone was speeding really fast, like going 80 kilometers an hour, if they slam on the brakes, the car's going to skid until it reaches a point where it can stop. So this makes sense that the faster a car is going, the more time it needs to stop. So it says determine the domain and range of this guy. Well, we can do that. So is it possible for speed to be less than 0? No. So we know that the domain of this thing is that x has to be greater than or equal to 0. We can also add a layer of complexity here. Is really if x is equal to our speed. So really instead of x we should be putting, let's just erase that, and we should be putting v. So let's change that first. Can the speed of a car really be anything that's greater than 0? Can it be 400 kilometers per hour? And the answer to that is maybe theoretically one day, but not the cars that we have today. So actually we have to really think about this. Can the speed be anything that's greater than 0? So first of all, let's change our x again to v. And the answer to that is no, v can't just be greater than or equal to 0. We got to think of some sort of maximum. So after a quick Google search, actually the world's fastest car has gone 270 kilometers per hour. Now let's say that you were coming up with this on your own without internet. Come up with something that's reasonable. So what do you think is a reasonable maximum, and just explain your reasoning until you have the tools to be able to research what an actual maximum would be. So we got to set a realistic maximum. So the minimum that this speed can be is 0, and a car's speed can be 0, so it can equal 0 because that just means it's stopped. And the maximum it can be, let's approximate it as 270 kilometers per hour. Okay, so we've approximated this. Oh, let's change this to, we've approximated, but this is much more realistic than the speed just has to be greater than 0, because that's not really possible. So let's do the same thing to our range. So instead of y, we're going to use d. So our stopping distance can be an element of R, meaning it can be any tiny little real number. The smallest stopping distance, according to our graph, is 0, and that makes sense. That's going to occur when the car's not moving at all. Then it doesn't need any space to stop. What's going to be the maximum stopping distance? Well, that's going to depend on the restriction that we put on our domain. So we approximated that the fastest a car can go. Now, really, cars like the cars that we have every day can probably go 180. So if you want to put 180 there, put 180. I just Google searched and said the fastest we can go in a car as of right now is 270 kilometers per hour. So we have to figure out if that is our fastest time, what would be our longest stopping distance? So we'd actually have to throw this guy into our equation. So if we do a quick calculation, our stopping distance of the fastest car in the world would be 0.06 times our velocity, which is 270 kilometers per hour squared. That would be 437.4 meters. So if this fastest car in the world was going a full 270 and we slammed on the brakes, it would be skidding for almost half of a kilometer until it came to an absolute complete stop. So based on our approximation of what our maximum is, again, if you had this question on an assessment where you couldn't use the internet, you're just going to approximate it. What's a reasonable answer? This is a pretty crazy answer, but we have some research to support it. So the stopping distance can be any element of all real numbers. The smallest it can be is 0. The biggest it can be is 437.4 meters. So there's our domain and range of this guy. So now let's take a look at part B. It says determine the equation for its inverse. What does it represent? Well, what the heck is going to be the inverse of this thing? So just go back to the definition of an inverse. So right now in this equation, we input a speed and output is the stopping distance. So the input is the speed, and the output is the stopping distance. So that's our original function. Our inverse is going to be, well, if we put in the distance, I want to know the speed. So let's start with our original equation. We have our distance is equal to 0.006 v squared. So I'm inputting the speed and I'm popping out the distance. That's our original equation. So I want the inverse, which is if I input the distance, I want the speed. So really this is just a grade 9 problem where this is just asking us to isolate for the other variable. I want speed given distance. So in this question, we're not going to swap d and v. So it's not really an inverse that they're asking us for. So if we have a real life situation, our textbook asks a lot of these questions where it says come up with the inverse, but really we're not swapping d and v because we can't, because d stands for the stopping distance and v stands for the speed. So these each have meanings and we can't just swap them. Before we were just dealing with x and y. They had really no meaning in our previous examples, so we can swap them and we're not breaking any rules, but we can't make this equation true if we were to switch d and v. So in an equation where d or our variables have meaning in the real world, we can't actually swap d and v. But just go back to what an inverse is. An inverse is going to be an equation so that the original input is now our output and the original output is now our input. So our original function, we inputted the speed, we got distance. I want to say, what if I input the distance? What's the equation for speed? So really this is just asking us to rearrange. So that's what we're going to do. So we're just going to rearrange for v. So rearrange and isolate for v. Isolate for v. So let's divide by 0.06 and divide by 0.006, and we're going to be left with d over 0.006 is equal to v squared. Oops, v squared. Here we go. We got to get rid of the squared by square rooting and square rooting. Okay, the question is, should we put a plus or minus? So the question is, can our velocity, which is our speed, be negative? And the answer to that is no. So we don't actually need to put a plus or minus in this case because our speed can't be negative. So we're just going to take the positive square root. And we're going to be left with our v, our speed, is equal to the square root of d over 0.006. So now we can input a distance and output will be speed, which is exactly what we wanted. Inputting distance, output would be speed. So now it asks us to come up with the domain and range of this inverse, and I say that with the quotation inverse, where we've found an equation so we can input distance and get our speed. So now our input is our stopping distance. So originally our input used to be our speed, now our input is our stopping distance. So we're going to write domain. Well, first of all, that's going to be our stopping distance. So our stopping distance can be any tiny little number, and let's cheat and look up here. We already figured this out. We said our stopping distance, the lowest is 0 and the highest is 437. So that's what we're going to write. So 0 is less than or equal to d is less than or equal to 437.4 meters. And how about our range? Well, now our output is our speed, so our range is our velocity. So we know velocity can be any tiny little number such that, we already have the answers up here. The lowest our speed can be 0, and the highest we approximated is 270 kilometers per hour, which is crazy fast. It's okay, so our lowest speed is 0, the highest speed is 270. So all we've done is we've switched the domain and range from the original function for our inverse function. All right, let's take a look at our last problem. It says determine the equation of the inverse relation for the surface area of a sphere. What does it represent? Determine the domain and range of the function. So we're given our equation of surface area. So a surface area is equal to 4 pi r squared. So our two variables are s for surface area and r is our radius. So here's our original function. So our original function, we input a radius and we get the surface area. So if we just make a little note here, originally we input the radius and output comes this the surface area of the sphere. So that's our original function, which means our inverse in quote means that if I want to input the surface area and get the radius. So that's what I want for my inverse function. So I know that I cannot, like when we're dealing with x and y, I can't just swap surface area and radius. That doesn't make any sense. The radius is not equal to 4 pi the surface area squared. So these two have properties that we cannot change, and so we cannot move these guys. So let's just sort of do our superficial inverse, which is that we're just going to rearrange this thing just like we would have done in grade 9. So that I can input a surface area and get the radius. So right now I'm inputting radius, getting surface area. So let's isolate for this radius. So that's what I'm going to make a little note about. We're going to isolate for r. So here we go. Let's get r by itself. So the first thing I'm going to do is I'm going to divide by 4 pi. And divide by 4 pi. So on the left we have our surface area divided by 4 pi is going to give us r squared, because 4 pi divided by 4 pi is going to cancel out. Okay, our next step is we've got a square root. So we're going to square root this side and we're going to square root this side. And the question is, do we take plus or minus the square root? So can the square root be positive and negative? Well, go back to r. Can r be positive, the radius? Definitely. Can r be negative? No, because it's a length. So also in this case, r can't be negative. So we're not going to take the positive and negative square root. We're just going to take the positive square root. So we have as our final solution for r, the surface area divided by 4 pi is equal to r. Okay, so here's our quote-unquote inverse. And our original function, remember, was our equation just isolated for surface area. So this is our original equation. So the question that I asked next is, what does this represent? Well, this just represents the same formula, just isolated for r. So this represents the functions rearranged so that the input is the surface area and the output is the radius. So I can input surface area and get the radius. The next question says determine the domain and range of both the functions. So let's start with our original function. So our domain of this guy here is our input, which is our radius. So what can our radius be? So we're going to say domain is radius, can be any tiny little number. Is there any restriction on a radius? So first of all, can a radius be less than 0? And that would be incorrect. No, we can't have -2 as a radius of a sphere. So we know that the radius can't be negative. Can it be 0? Well, think about it. If the radius was 0, we wouldn't have a sphere at all. So what are we even talking about? So we can't find the surface area of something that doesn't exist. So let's say that the radius has to be greater than 0. Is there some sort of upper bound? So in the previous example, we were bound by technology. How fast can a car really go? Well, the maximum speed is 270. Maybe you came up with your own idea. Technically, we could have a sphere the size of the universe, which is infinitely large. So really, the radius just has to be greater than 0, and that's our only restriction. So take a look at our range now. So for our range, that's our surface area. So our surface area is an element of R, and if the radius has to be greater than 0, then the surface area has to be greater than 0, and it can also be infinitely large. So now, for our quote-unquote inverse, our domain and range are just going to be swapped. Remember that our domain now is going to be our surface area. That's our input. So surface area is an element of R, such that surface area is to be greater than 0. And our range, that's our output. Now that's our radius. And we already figured out that radius can be any tiny little number, but it has to be greater than 0. Oh, by the way, surface area also can't be equal to 0 if we're not letting our radius equal 0. That's something else to note. Okay, so now you know all the basics. Now it's time for practice. We have our worksheet, we have our homework in the textbook. Go for it.